Bismillahirrahmanirrahim. Today we will talk about chapter 25, current, resistance, and electromotive force. In the first lecture of this chapter, we will discuss the current, the resistivity, and the resistance. In the second lecture, we will talk about electromotive force and circuits. And then we will finish by the energy, power, and the power in the electric circuits. Let's start by the definition of the current. In the absence of an external field, electrons move randomly in the conductor. If an electric field exists near the conductor, its force on the electrons imposes a drift velocity. So here we will talk about the drift velocity of the electrons imposed by the electric field. A current is any motion of charge from one region to another region. So this is the definition. Any motion of charge results in electric current. The current intensity is defined by dq over dt. Q is the charge, its unit is C, coulomb. T is the time, its unit is second. So the current is coulomb divided by second, which is equivalent to ampere. So one coulomb divided by 1 second is equivalent to 1 ampere. Good. The current can be produced by positive or negative charge flow, but the conventional current is treated as the flow of positive charge. Let's take these two examples. You see here that we have electrons, and these electrons are moving leftward. The current in this case is rightward. Why? Because we said the conventional current is treated as a flow of positive charge and opposite to the negative charge. In the second example, we have positive charges are moving rightward, and the current, of course, is moving rightward because it's associated with the motion of positive charge. This point is very important. Okay, the conventional current is treated as a flow of positive charge, and it's opposite to the direction of the negative charges. Positive charge will move with the electric field. Electrons move in oppositions. And this is evident because the force is equal to Q multiplied by the electric field. If Q is positive, in this case, E is parallel to the electric force. If the force if Q is negative, in this case, F and E are anti-parallel. Is it okay? Very good. So we are done. The moving charges in the metals are electrons. So in the metals, the direction of the current is opposite to the direction of the electrons. Now we will talk about the microscopic model of the current. If we consider a conductor with cross-sectional area A and has a cylindrical form, if we consider that Vd is the drift velocity of the charge carriers, then these charges, they will travel a distance delta x in a time delta t. As we know, V is equal x. Yeah, as we said, the speed is equal x over t. So it's delta x over delta t, the average. Okay, so we can say that delta x equal v multiplied by delta t. The volume element that contains the mobile charges flowing through the surface A during a time delta t is equal A multiplied by delta x. So this is this surface area multiplied by this distance delta x. Okay, so, and we know that delta x is Vt delta t. So we can say that the volume is equal A Vd delta t. Now, if we define the number of charge per unit volume, small n, the number of charge per unit volume will be equal to the number of charge of mobile charges in the volume divided by the volume. And we can define also, we can say also that the number of mobile charges in the volume element is equal the number of charge per unit volume multiplied by the volume. And we know that the volume is the following AVD delta T. So we can say that capital N, the number of mobile charges in the volume, is NAVD delta T. We are done. This is our equation. Now, if we move to the charge in volume element, if each charge carrier has a charge Q, then the charge in the volume element delta Q is equal to the number of mobile charge in the volume element multiplied by the charge per carrier. And we can say that delta Q is the number of charge multiplied by the charge of the carrier Q. And we know that N from the previous slide is equal N A VD delta T. If we multiply here by Q, we will multiply by Q, and we will get delta Q. So now, if we divide by delta T in the two sides, what we're gonna get? We will get the average current. So the average current will be NAVDQ, and we are done. So if the charge carriers are electrons, then Q is equal to E in absolute value, of course. So the current will be NEVDA. Good, we are done. This is the equation that we want to introduce. The average current in the conductors is equal NEVDA. A is the surface area of the conductor, VD is the direct velocity, and E is the unit charge 1.6 times 10 power negative 19, and N is the number of charge per unit volume. We take an example. We consider positive and negative charges moving horizontally through the four regions shown in the figure below. Which of the following ranks the current magnitude in these regions from the lowest to the highest? Let me make a short review at first. We said that the conventional current is treated as a flow of positive charges. And of course, it's opposite to the negative charges. Now, in these four examples, we have some charges. Some of them are positive, some of them are negative. So the unit current is with the positive charge and opposite to the negative charge. So we can say a positive charge moving to the right contributes the same current as negative charge moving to the left. Why? Because the current is associated with the motion of the positive charge. And we can say that the graph 1 or the figure 1 represents 5 currents, 5 units of the current. To the right, all of them. Why they are to the right? For the electrons, we have 2 electrons, so they will contribute with the 2 units of current to the right, and we have three positive charges, so they are contributing with 3 unit current to the right. So the total here, it will be 5 units, 5 units of current to the right. What about B? B, we have 4 to the left, so 4 units of I to the left. What about C? C, we have 2 to the right, positive charges to the right, 2 negative charges to the left, so the total will be 4 units of current to the right. And what about here? We have 2 units of current to the left because we have negative charges. Now we can rank from the least to the highest. From the least, which one is the least? Is D. Let's check the answer A is wrong, wrong, wrong. So D, yeah. And then we have 4 units to the left, 4 units to the right. So whatever the direction, because here we're talking about magnitudes, so we will take B equal to C. And here we have 5 units, so it's smaller than A. And the correct answer is is D. Let's move to the second example. The 12 gauge copper wire in a typical residential building has a cross-sectional area of 3.31 times 10 power negative 6 meters squared. If it carries a current of 10 ampere, what is the drift speed of the electrons? We assume each copper atom contributes 1 free electrons to the current. The density of the copper is 8.95 gram per centimeter cube, and its molar mass is 63.5 gram per mole. You see here that we have an information about the area. We have information about the current. But we don't have information about it's asking about the drift speed. What will be the drift speed? As we know in the previous example, I equal N E VD multiplied by the area. That means VD equal I divided by N E multiplied by the surface area. We have information about I, we've already given 10. We have information about the area. We know the E, but we don't know the N. N is the number of charge per unit volume, and it's equivalent to Avogadro number, which is the number of atoms per unit, per mole, number of atoms per mole of atoms per mole divided by the volume of 1 mole. Good. The volume of the one mole. However, the volume of 1 mole is equal to the mass of 1 mole divided by the density. So we can say that the number of atoms, the number of atoms per unit per unit volume is equal to Avogadro number divided by the mass m multiplied by the density rho. This is the number of atoms per unit volume. Okay. However, each atom contributes with 1 free electron. So we can say that the number of atoms per mole, the number of atoms per unit volume is equal to the number of electrons per unit volume. And we are done. So we can say that N equal Avogadro number, which is equal to 6.023 times 10 power 23 multiplied by the density 8.95 divided by the molar mass 63.5 for the copper, and we're going to get 8.49 times 10 power 22. 8.49 times 10 power 22 atom or electron atom per what? Per centimeter cube, or electron per centimeter cube. Very good, because one atom is contributes 1 free electron to the current. We are done. Let's continue. However, you see here that the unit is a centimeter cube, but the international unit is meter cube. So we can say that N equal 8.49 times 10 power 22 electrons divided by 10 power negative 6 meter cube. Why? Because 1 centimeter cube is equivalent to 10 power negative 6 meter cube. And we're going to get 8.49 times 10 power 28 electron per meter cube. We are done. Now we can calculate our drift velocity to be I over NEA. So it's equal to 10. The current is 10 in the question. 8.49 times 10 power 28 multiplied by 1.6 times 10 power negative 19 multiplied by the cross-sectional area 3.31 times 10 power -6. And we're going to get VT equal 2.22 times 10 power -4 meter per second. We are done. So you see here that we have a very small speed in the order of magnitude 10 power -4 meter per second, small speed. So the electrons in the copper wire are moving with a very small speed. Okay. Now we move to the current density. We consider a conductor of cross-sectional area A carrying a current I. The current density J in the conductor is defined by the current per unit area. So J is the density, which is equal I divided by A. I in the previous slides is equal N E VD A. If we divide here by A, we will get the density, and here also we divide by A, and we will cancel this A. So J is equal NEVD. NEVD. This is when we talk about electron. In general, it's equivalent to NQVD. Okay, we are done. Its unit is ampere per meter squared. And the current density J and an electric field E are established in the conductor whenever potential difference is maintained across the conductor. In this case, we can say that J equal the current density equal a constant called sigma conductivity multiplied by E, and this is Ohm's law for the conductors. So sigma is the conductivity. Let's continue. Another formula of Ohm's law. If we consider a segment of straight wire of cross-sectional area A and the length L, a potential difference delta V is maintained across the wire. This creates an electric field E and a current I. Of course, we know that E equal delta V over L. From this equation, delta V equal minus EDS. In our case, we will take the absolute value, and we're going to get E equal delta V over L. That means the current density J is, as we said in the previous slide, sigma E, and E equal delta V over L. Okay? On the other side, J equal I over A. So that means delta V will be equal L over sigma A multiplied by I. Very good. This quantity is called the resistance R. So delta V will be equal Ri, where R is equal L over sigma A from one side, and it's equals delta V over I from the other side. Okay? If we want to plot this, this equation, delta V I as a function of delta V over R, so what we're going to get? We will get a straight line with the slope over 1 over R, with the slope equal 1 over R. And this equation is called Ohm's law. So the potential difference across any conductor or resistor is equal Ri. R has a unit ohm. 1 ohm is equivalent to 1 volt divided by 1 ampere. The materials that obey to Ohm's law are called ohmic material. For example, the metals. The metals are ohmic materials. And here we have a straight line. I as a function of delta V is a straight line. However, some other materials, they do not obey to Ohm's law. So they are called non-ohmic materials. So non-ohmic materials, that materials do not obey to Ohm's law, are called non-ohmic materials, example, the semiconductors. And this is the curve for I as a function of delta V. So we don't have a straight line. The current potential difference curve for non-ohmic material is not linear. Okay, the current potential difference curve of ohmic material is linear, but for the non-ohmic material is not linear. Let's discuss now the conductivity. We saw in the previous slide that R equal L over sigma A. That means sigma is 1 over R multiplied by L over A. The unit of the sigma, the conductivity, is 1 over ohm meter, or ohm minus 1, meter minus 1, power minus 1. Okay, now we will define something that we call resistivity. The resistivity is 1 over sigma, so it's equal RA over L. This is our resistivity. The unit of the resistivity is ohm multiplied by meter. Keep in mind that the resistivity depends on the material. On the material, that means each material has a value of resistivity. For example, the copper has a resistivity and the aluminum has resistivity, iron has a resistivity, but it's independent on the shape, on the length of the material. Depends on the material and the temperature. We will discuss in details these two sentences. You see here that for the metals, each metal has a value of resistivity. It's like a fingerprint of the material, and we have to specify at which temperature, because the resistivity depends on the temperature. And this is for the alloys, and this is for the semiconductor, and this is for the insulators. You see that the resistivity of the conductors or the metals is very small, in the order of 10 power negative 8. But for the conductors, it's very high, 10 power 14, 16, 13, 11, okay? Good. But for the semiconductors, it's around 10 power negative 5, and so on. A question: calculate the resistance of an aluminum cylinder that is 10 centimeter long and has a cross-sectional area of 2 times 10 power minus 4 meters squared and the resistivity 2.82 times 10 power minus 8 ohm meter. This is our resistivity. This is our cross-sectional area, and this is our L, the length of the wire. Okay, so what will be here the resistance? He's asking about calculate the resistance. The resistance, as you know, is rho L over A. We have an information about rho. Yeah, it's 2.82 times 10 power minus 8 multiplied by L, which is 0.1 meter, multiplied by divided by the area, and we are done. Do the same calculation for a glass cylinder of the same dimensions and has a resistivity 3 times 10 power 11 ohm meter. You see here that the resistivity of the aluminum is 10 power minus 8, very small. But for the glass cylinder, since it's an insulator, so it's very high, 10 power 10 ohm meter. This is the first thing. The second thing, the resistivity depends on the material. For the aluminum, it was a value. For the glass cylinder, has another value. The same calculation gives R equal rho multiplied by L over A. So we can get the resistance is very high, 1.5 times 10 power 13 ohm. It's very high. And this is low. Okay, good. A second example, calculate the resistance per unit of length of 22 gauge nichrome wire, which has a radius of 321 millimeter and resistivity 1.5 times 10 power negative 6 ohm meter. This is the radius. He's asking about the resistance. As you know, the resistance is rho L over A. But here we don't have the A. A equal, because it's cylindrical, so it's equal by R squared. R is the radius. And we are done. So we can get the resistance per unit of length is rho over A. And we can divide rho 0.321 millimeter. Of course, we have to convert, rho is 1.5 times 10 power negative 6 ohm meter divided by the area by R squared, and R must be converted to meter. That means multiply by 10 power minus 3. And we can get that the resistance per unit of length is equal to 4.6 ohm divided by meter. If a potential difference of 10 volt is maintained across 1 meter length, so L in our case is 1 meter, of nichrome wire, what is the current? As we know, delta V equal Ri. That means Ohm's law, that means what is the current? That means I equal delta V over R. However, we don't have this R, but we have R over L. In our case, L is equal 1, so that means R over L equal 4.6 ohm. 4.6 ohm, that means the current is 10 divided by 4.6, which is equivalent to 2.2 ampere. We are done. Let's continue. Variation of resistivity with the temperature. As we said in the previous slides, the resistivity depends on the material and depends on the temperature. The resistivity rho of the materials vary approximately linearly with the temperature, according to the following expression: rho equal rho naught, factor of 1 plus alpha, T minus T naught. Rho is the resistivity at a certain temperature. Rho naught is the resistivity at the reference temperature. It's usually taken as 20 degrees as a reference. Alpha is the temperature coefficient of resistivity. T is a certain temperature. T naught is the reference temperature. The temperature coefficient of resistivity alpha can be gotten from the following. From this equation, so alpha, it's 1 over rho naught multiplied by delta rho, that means rho minus rho naught, over delta T, that means T minus T naught. And we are done. Based on the variation of resistance with the temperature. Since we know that the resistance is rho L over A, so it depends on rho. Rho depends on the temperature, so that means R depends also on the temperature according to this equation. R equal R naught, factor of 1 plus alpha T minus T naught. Based on the variation of the resistivity as a function of the temperature, we have different types of material. In this first figure, the resistivity increases with the temperature. So these kind of materials are called metals. The resistivity increases with the increasing of the temperature. And the second type, the resistivity decreases with the temperature. In this case, we talk about semiconductors. And the third case, we have resistivity 0 below a critical temperature. After that, it's increasing with the temperature. This kind of material are called superconductors. At a temperature below critical temperature, the resistivity is 0. After that, the resistivity below the same shape as the conductors, as the metals. Example, a platinum resistance thermometer, a resistance thermometer, which measures the temperature by measuring the change in the resistance of the conductor, is made from platinum and has a resistance of 50 ohm at 20 degrees. When immersed in a vessel containing a melting indium, that means a high temperature. Okay, its resistance increases to 76.8. So we have T naught is 20 degrees, R naught, the resistance at the reference temperature 50, R at a certain temperature 76.8 ohm. We have the temperature coefficient of resistivity 3.9 times 10 power minus 3. And the question is, what is T? We write the equation of R from this slide. R equal R naught factor of 1 plus alpha T minus T naught. And we can get that alpha equal 1 over R naught delta multiplied by delta R over delta T. And we can get T equal 157 degrees. Okay, so we can write that 76.8 equal 50 ohm factor of 1 plus alpha 3.9 times 10 power to 3 factor of T minus T naught. So an equation with one unknown, so we can solve this equation on T. Okay, good, we are done. Let's continue. Now we have some class activities. Question 1, 2 copper wires of different diameters are joined end to end, and the current flow in the wire combination. When electron move from the large diameter to the small diameter, What happened to the drift velocity? As you know, the drift velocity is I over N E A. What happened to the diameter? The diameter is decreasing, so that means the radius is decreasing. That means the area is decreasing. When the area is decreasing, the drift velocity is increasing. Their speed is increasing. Electrons in an electric circuit passes through a resistor. The wire has the same diameter on each side of the resistor. Compared to the drift speed of the electrons before entering the resistor, the drift speed of the electrons after leaving the resistor is the same. Okay, it will be slowing down, then speeding up. Good. The electrons in an electric circuit pass through the resistor. The wire has the same diameter on each side of the resistor. Compared to the potential energy now, we talk about the potential energy of an electron before entering the resistor. The potential energy of the electron after leaving the resistor would be less. Why it's less? Because some of the energy will be lost in the resistance. Question 4, a certain wire has a resistance R. Another wire has the same material. We are talking about same material, that means same resistivity. Has half length of the and half diameter of the first wire. The resistance of the second is what will be? You know that R equal rho A over L. What happened? This is R naught. What happened to the length is divided by 2. So R equal rho L over 2, L naught over 2. And what happened to the diameter? It's the half. We know that the area equal pi R squared, or pi D over 2 over 2 squared. So what we're going to get? We will write here pi D naught over 2 because the diameter also is divided by 2, 2 multiplied by 2 power 2. So what will be? It will be rho pi d squared naught over 2 over L naught. This 2 it will be times 2, and we have over 2 squared. So what we're going to get? We will get R equal R naught divided by 2. So what happened to the resistance? It will be divided by 2. And we are done. Last example. What is the effect on the current in the wire if the voltage across the wire is doubled and the resistance is cut in half? Here we are talking about current, potential difference, resistance. So we don't have anything else than Ohm's law. What happened to the current? Okay, now what happened to the current? The current is when the potential difference is doubled. So here we have 2 delta V naught. And the resistance is cut in half, R naught over 2. So it will be delta V naught over R naught multiplied by 4. Okay, so it will be I naught multiplied by 4. So the current decreases by a factor of 4. No, it's increasing by a factor of 4. The current decreases by a factor of 2. No, the current stays the same. No, the current increases by a factor of 2. The current increases by a factor of 4, and we have the correct answer because it would be I naught multiplied by 4. We are done. Thank you so much, and see you in the next recording.